So in the previous lecture, we stopped at this stage. We found out h prime of t, which is equal to minus q by m a dot p. In this lecture, we'll be continuing with this derivation. We will simplify this equation by substituting the value of a in its plane wave notation. That is this one. So this is vector potential's plane wave notation. That is a naught into e raised to I k dot r minus omega t plus e raised to minus I kr minus omega t epsilon cap. And then we substitute it back to this equation in place of this a, and we get it like this. So the new Hamiltonian h prime equation is this one. Now we'll do a small approximation. In order to do that, let us suppose you have a molecule or an atom, and the size of an atom or the molecule on which the light interact is very small compared to the wavelength of light. Let's say the molecule is around 1 nanometer, and the wavelength we are taking the case of UV visible spectroscopy. So the wavelength itself starts from 200 nanometer up to 800 nanometers. So the size of the molecule is so small in comparison to the wavelength. That means effectively you don't see the wave which goes up and down because of the small portion of the light. The wave is not changing at all. This means 1 by lambda is equal to 0, and lambda tends to infinity, right? That means k is equal to 2 pi by lambda. If 1 by lambda is equal to 0, k is also equal to 0. That means here the k term in this equation, that k term vanishes, right? Because k is becoming 0 due to 1 by lambda becoming 0, and that is lambda's infinity. Fine, you just have to substitute it, remove the k dot r term and rewrite the equation. Now you got this, and e raised to I theta plus e raised to minus I theta is nothing but 2 cos theta. So we can write it as minus q by m a0 2 cos omega t a dot p, right? Also we can write e naught to be equal to minus 2 a naught omega. Here we have 2a, but we don't have omega, so multiply and divided by omega, so it's omega divided by omega, and then this whole term becomes e naught, right? Just write it minus 2a omega. Yeah, and you can rewrite it as h prime of t is equal to minus q by m, sorry, minus is also gone, e naught cos omega t e cap dot p cap. Oh sorry, I missed out in omega, so there's omega here. Yeah, so it's like q e naught by m omega q cos omega t epsilon dot p. And we know epsilon naught is nothing but the unit vector of the electric field, and E naught is the maximum amplitude of the electric field. Fine. Here you can see that h prime of t depends on single charge, but molecule comprises of multiple charges. So we can modify the h prime of t equation to be you take q inside, you take summation of it, and the rest of the terms will be outside. So it will look like this: E naught divided by omega summation cos omega t summation of n qn divided by mn. So for collection of charge particles, this is called the dipole approximation. And this Hamiltonian over here is the Hamiltonian for electric dipole. So we can write it as electric dipole Hamiltonian for charge particles, Hamiltonian for many charge particles. Okay, we will stop here in this lecture and continue in the next class.